Till now, we introduced and discussed a number of basic system properties like static versus dynamic, then linear systems and non-linear systems, right? Then time varying systems and time invariant systems, right? Then causal systems or non-anticipatory systems, then stable systems and unstable systems, then inverse systems, invertibility and inverse systems. So these are the properties that we have discussed. And out of all these properties, this linearity and time invariant, okay, play a fundamental role in signal and system analysis. Okay, due to some 2-3 major reasons, especially 2 major reasons. The first reason is many physical processes possess these properties, and thus the physical processes can be modeled as a linear. Many physical processes can be modeled as a linear time invariant system. So in short, this is called a LTI system, okay, linear time invariant systems. In addition, the second reason is, in addition, LTI systems can be analyzed in considerable detail, providing both insight into their properties so what are the properties of the systems, and a set of, also we have some set of powerful tools okay. So later we will study, there are many tools, like if the signal is periodic signal, if the signal which you are applying to the system which is periodic signal, then you can use a continuous time Fourier series, and if it is a discrete periodic signal, then you can use discrete time Fourier series. If it is aperiodic signal, use continuous time Fourier transform. Then if it is a aperiodic discrete time signal, then use a discrete time Fourier transform. Again you have DFT, discrete Fourier transform. Then you have Laplace transform, then Z transform. So like that we have many tools. So all these tools we can use very nicely, and we can find the properties and behavior of the system only for LTI systems, not for other systems, okay. So that form the core of the signal and the system analysis. Because of this tool only, our signals and system analysis becomes very easy, and it becomes very useful for us. It makes our life very simple. So these are the 2 main reasons that we study LTI systems. The first reason is many physical systems possess this property. Many physical system, practical system possesses this property, many physical processes. And the second one is, we will study their properties and system behavior by using a set of powerful tools. So these are the 2 reasons that we consider linear time invariant system. So the principal objective of this course is to develop an understanding of these properties and tools. So what are the properties of the systems? and then understanding the tools. Mainly we will spend time on these two only. These two are the primary objective. The main objective of this course. So in this lecture we begin the development by deriving and examining a fundamental and extremely useful representation of LTI system. The input is x of n and the output is y of n. Let's say we considered discrete time systems by introducing an important class of these systems. One of the primary reasons LTI systems are amenable to analysis is that any such system responses or any such system possesses the superposition property. Since it is linearity, then it possesses the superposition principle. Because when we discussed the linearity of the system, that time we said the linearity holds only if homogeneity and superposition, these two are satisfied. As a consequence, if you can represent the input to an LTI system in terms of a linear combination of set of basic signals, okay, then we can use a superposition to compute the output of the system in terms of its responses to these basic signals. Okay, so you have a system, then this is my input x of n, and this x of n contains, like let's say there are 3 pulses 0, 1, 2 like this. Now what you do is you represent this x of n in terms of basic pulses. When I say basic pulses, what are the basic pulses? Either del of n or u of n, or you can use r of n, any one which is appropriate, more appropriate, and represent this and find out the response of y of n. You first apply this guy alone and find what is the response. Then you send this guy alone. Okay, so first you send this guy alone, find the response. Then second, allow this guy and find the response. Again send this guy and find the response. Therefore the total response is sum of all these 3 responses. Therefore the superposition principle plays a vital role, or it is the very important property on which we can now develop the theory. Okay, therefore the important characteristics of the unit impulse is used here. Okay, so the del of either del of n in the case of discrete time domain, or del of t in the continuous time domain. This impulse, this is called a unit impulse, right? This unit impulse plays a very important role. Okay, so that a very general signals can be represented as a linear combination of delayed impulses, that we will see. For example, if you take this guy, let me redraw the figure again here. Let's say I have the pulses like this. Let's say 0, 1, 2, and this is n, and afterwards it is 0 like this. This all are 1, 1, 1. Now if you take this pulse alone, I can draw like this, right? So this pulse is, how do you denote? Let's say, let me draw like this. I have the pulses like this. This is 2 and this is 3 and this is 1. Let us assume like that. Now the amplitude is 2, x of n. Now you consider this pulse alone. This pulse alone. So how do you write that pulse? This pulse is located at n equals 0 with magnitude of 2. Therefore, it is an impulse with magnitude 2 sitting at n equals 0, therefore del of n, that's it. Okay. Now you take the second pulse. That second pulse is like this. At n equals 1 and rest of the points are 0 and the magnitude is 3. Then how do you describe this pulse? 3 times del of not n, it is n minus 1, it is shifted by 1 unit. Now how do you describe this guy? This guy is sitting at, let's say this is 0, 1 and 2, it is sitting at 2 with the strength of 1. So therefore the strength is 1, so you put 1 here and del of, now the impulse is shifted by 2 units, so del of n minus 2. Therefore this x of n I can write as del of n plus del of n minus 1 plus del of n minus 2, right. So from this exercise what we understood is any arbitrary signal can be represented as a linear combination of delayed impulses. See, this is delayed by 1 unit, this is delayed by 2 units. Okay, this fact together with the properties of superposition. Okay, see, this is del of n minus 2, 3 into del of n minus 1 and here 2 times del of n. This all you know combine together, so that is you are using superposition principle. Okay, delayed impulses together with the properties of superposition and time invariance, LTI, time invariance will allow us to develop a complete characterization of any LTI system in terms of its response, okay, to a unit impulse. Such a representation referred to as the convolution. We will derive this formula. Convolution sum formula, okay, in the discrete time case, and the same procedure or same formula in the continuous time case is called convolution sum formula. Convolution sum formula in the case of continuous time case. Okay, and these two formulas, convolution sum and convolution integral, provides a considerable analytical convenience in dealing with the LTI systems. So using this formula you can find out the response of the LTI system, what is the output for an arbitrary input signal. We don't know, it can be any input signal. Okay, so the convolution sum and the convolution integral we will use to characterize and to examine some of the other properties of LTI systems also. Okay, and later on we consider the class of continuous time systems described by linear constant coefficient equations. Okay, this is described by, as I already told you, linear constant coefficient equations. Okay, it's a discrete time counterpart. It is explained by or described by linear constant difference equation. Linear constant difference equation. Okay, so now let us try to see how the discrete time signal is represented in terms of impulses. More formally we will see, already I told you, but anyway we will see more formally. The representation of discrete time signal signals in terms of impulses. This is what we are going to look at now. Okay, so now we will consider discrete impulses, not continuous time impulses, discrete time impulses. Later on we will consider the same thing for the continuous time signal also. Let us take the discrete impulses del of n. Okay, so this discrete time unit impulse can be used to construct any discrete time signal that you think of. For example, let me consider a signal like this. Let's say this is 2 at n equals 0 and maybe 1.5, then this is 1, then again let me put minus 2 like this. This is 1 and this is 2 and this is 3. It keep on goes. Let's say these all are zeros. Right. So now I have how many non-zero pulses? 1, 2, 3, 4 pulses are there. Now you take one pulse at a time and see how we can describe mathematically. It is located at 0 with the unit 2. I am taking this pulse here, this pulse alone. As I said, this pulse alone can be four pulses totally. So this is described as 2 times del of n. Now you consider this guy alone, then it is, maybe I will draw here, located at 1 with the amplitude of 0.5. This is 0, minus 1, 1, 2, 3 and so on. This is n, right? Now the amplitude is 1.5, therefore this is denoted by del of n minus 1. It is shifted by 1 unit. What is the strength of the impulse? 1.5. Similarly, you can write this guy, and that will be like this. At n equals 2, its magnitude is only 1 unit. This is 1, this is 0, this all places under 0. Like this you can represent. What about this one? It is again, the magnitude is 1 times del of, now the delta function is located at 2, therefore n minus 2. I have one more impulse, it is located at 3. So this point is 3, 2, let's say this is 3, this is 2, 1, 0. At 3 the magnitude is minus 2, this guy. Okay, therefore at 3 the magnitude is minus 2. Minus 2. Now therefore this is del of n minus 3, but the magnitude is minus 2. Therefore any arbitrary signal can be represented in terms of this impulse functions. Okay, so this is the picture representation. Now let us write this guy in mathematical way. Now by the way, what is this one? This one is x of 0. What is this guy? X of 1. What is this guy? X of 2. What is this one? X of 3. Okay, so therefore what is x of 0 now? 2. X of 1, 1.5. X of 2, 1. X of 3, minus 2. Now we will come to this place. This is 2 times x of delta of n, right? So this 2 is nothing but, if you look at here, 2 is equal to x of 0. Therefore, this I write as x of 0 times del of n. Please convince yourself. And now, if you look at here you have 1.5 delta of n, and this 1.5 is nothing but its amplitude at n equal to 1. Therefore, the 1.5 I can write as its value, I mean in terms of by x of 1. Therefore, this one I can write as x of 1 times del of n minus 1. By the way, this is a value, x of 1 is a value of 1.5, that's why. Now look at this impulse now. It is 1 multiplied by del of n minus 2. What is this 1? This 1 is here. X of 2 is equal to 1. Therefore, I will write this as x of 2 times del of n minus 2. Okay. Now, again if you look at here minus 2, and this minus 2 times del of n minus 3. Now, you come back here, minus 2 is here, and minus 2 is equal to x of minus 3, this one. Therefore, this minus 2 I can write as x of 3 times del of n minus 3. So, finally, I have x of 0 times del of n, comma x of 1 times del of n minus 1, comma x of 2 times del of n minus 2, comma x of 3 times del of n minus 3. So, I have 4 representation, 1, 2, 3, 4, and this corresponds to n equals 0, and this corresponds to n equals 1, and this corresponds to n equals 2, and this one is n equals 3. Therefore, each impulse is scaled, okay, and that scaling on each impulse equals the value of x of n, right. Now, in the original figure, your x of n is like this. This is where is the figure? Yeah, 2 1.51 minus 2, 2 1.51 minus 2, like this. What is this? This is x of n now, right. Now, this x of n is written in terms of these guys, x of 1 times del of n minus 1, like that. Now, you take this alone now, x of 0 times del of n, x of 0 times del of n is equal to x of 0 when n equals 0, and 0 when n not equals 0. I can write like that. Convince yourself from the definition of your impulse function, because the del of n has a value only when the argument is 0. Okay, for a discrete time case, the delta function has the value only when the argument is 0, no positive, no negative, nothing, no stories. Okay, whenever the argument is 0, then it has non-zero value, that is unity, its magnitude is unity. Therefore, since it n equals 0, then you can write like this. When n equals 0, what happens? This del of 0 becomes 1, that is why I did not write here. I can put del of 0, again this is equal to 1, that's why. Similarly, you take this guy, so that will be equal to x of 1 times del of n minus 1. Again, when the argument is 0, then I have the non-zero value. I mean 1. When will this argument become 0? When n equals 1. Therefore, this is equal to x of 1 times when n equals 1, when n equals 1, then del of 0 when n equals 1, or else 0 when n not equal to 1. Now what is del of 0? Del of 0 is equal to 1. Therefore, this I can write as x of 1 times x of 1 when n equals 1 and 0 n not equal to 1, n is not equal to 1. Similarly, you can write x of 2 times del of n minus 2 is equal to x of 2 times del of 0, or no need to write del of 2, just leave it, when n equals 2 and 0 when n not equals 2. That's it. Therefore, sum of these all sequences, let me write down x of 3. X of 3 times del of n minus 3 equals x of 3 when n equals 3 and 0 when n is not equal to 3. Therefore, the sum of these 4 sequences, like sum of these 4 sequences, this sequence, this sequence, this one and this one, this 4 equals, if you sum, then this is equals x of n. Okay, that is your x of n. Therefore, in general, x of n can be written as x of 0 times del of n plus x of 1 times del of n minus 1 plus x of 2 times del of n minus 2 plus x of 3 times del of n minus 3. Now, the x of n is given here. So, this is 2, 1.5, 1, minus 2, and this value is 3, this is 2, 1, 0, and this is n, right. Now, you substitute n equal to 0, n is equal to 0, then x of 0 is equal to x of 0 times del of 0 plus x of 1 times del of minus 1, right, plus x of 2 times del of minus 2 plus x of 3 times del of minus 3. Now, if the argument is negative, then that delta will be 0, and this also 0, this also 0. The only thing which is non-zero is this guy, that is equal to 1. 1 times x of 0, it is x of 0. Therefore, the left hand side is equal to right hand side. We got the result. Similarly, when you substitute n equals 2, then x, let me put n equals 1, no problem. When n equals 1, then x of 1 is equal to same thing in this equation. Okay, x of 1 times del of 1 plus x of 1 times del of 0 plus x of 2 times del of minus 1 plus x of 3 times del of minus 2. Now, again if you look at del of 1 is 0, don't say positive argument. Okay, if the argument is 0, then it is non-zero. If the argument is non-zero, then it is 0. This guy is equal to 1, it is not crossing. This is equal to 1. Okay, and because of this negative argument, this goes to 0, and here also negative argument in the delta function, it goes to 0. So, the only term which is left now is x of 1 times del of 0 equal to 1. Therefore, x of 1 is equal to x of 1. Similarly, you can prove n equal to 2, n equal to 3, and so on and so forth, right. So, any arbitrary sequence can be represented in terms of this discrete time unit impulse. It can be any sequence, it does not matter. So, in compact form I can write this as sigma. It starts from 0, therefore, let me put k is equal to 0 to it goes up to 3, therefore 3 x of k del of n minus k. Okay. Therefore, I can write x of n is equal to summation of k is equal to 0 to 3, then x of k del of n minus k. In compact form we can write, okay, in a more compact form. Substitute k equal to 0, then you will get x of 0 times del of n, k is equal to 1, then x of 1 times del of n minus 1. Substitute k is equal to 2, then x of 2 del of n minus 2 plus substitute k equal to 3, then x of 3 times del of n minus 3. So, I started with the sequence x of n, some arbitrary sequence, and that arbitrary sequence can be denoted by weighted sum of impulses. Okay. Therefore, this procedure represents any arbitrary sequence as a linear combination of shifted unit impulses. Okay. So, I am taking the linear combination here. So, when I say linear combination, what we mean by that? A times x of t plus b times x2 of t and so on, right? This is called a linear combination. Similarly, this del of n is weighted by x of 0, and here del of 1 is weighted by x of 1. Del of n minus 2 is weighted by x of 2. Del of n minus 3 is weighted by x of 3, and this all 4 signals are added. So, it is kind of no superposition. So, linearity principle we are applying here. Therefore, any arbitrary sequence can be represented as a linear combination of shifted unit impulses. Why is it shifted unit impulses? Here I have del of n, here I have del of n minus 1, here 2 times shifted unit impulses, and here I have 3 times shifted unit impulses. Okay, where the weights in this linear combination are x of k, this one. This is the weight. Okay, let me take one more, little bigger example. Sorry. It is a textbook example. Let me have a sequence like this. Like this. Let us say this point is 0. At 0 I have the magnitude like this, and at 1 I have like this, and at 2 I have like this, at 3 it is like this, and 4 it is like this. Again it repeats. Maybe it is like this, 3, then like this, then like this, then like this, like this. Again it repeats. So, I do not want to draw indefinitely. Similarly, in the left hand side also. Okay, in the left hand side, let us say minus 1, minus 2, yes. Like this, then it goes like that. This is 0, 1, 2, minus 1, minus 2. Let us consider between minus 2 to plus 2, this one. And how do you describe this guy? X of minus 1 times del of n plus 2, it is advanced. How do you represent this guy? X of 0 times del of n. How do you represent this guy? X of 1 times del of n minus 1. And what about this one? X of 2 times del of n minus 2. Okay, again we know the definition. What is x of minus 1 or minus, and this one is x of minus 2 times del of n plus 2. So, x of minus 2 times del of n plus 2 is equal to, as we did before, x of minus 2 when n equals minus 2 and 0 when n is not equal to 0. Similarly, you can write x of 0 times del of n, and again this is equal to x of 0 when n equals 0 and 0 when n is not equal to 0. Therefore, the sum of these 5 sequences, the first sequence, second sequence, this third sequence, fourth sequence, and one more is here, this guy, fifth sequence. There are 5 sequences. Okay, in this figure equals x of n for n ranges from minus 2 less than or equal to n less than or equal to 2, because initially we considered this interval. Therefore, more generally, by including additional shifted scaled impulses, because from this side I have many more impulses up to it goes up to infinity. The left hand side also I have many more impulses. Therefore, in general, let me call this is my x of n. This x of n I can write as x of n is equal to, the sequence starts from infinity, x of n minus infinity, by the way, minus infinity del of n plus infinity, advanced version, plus goes dot 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 dot, then x of minus 3 del of n plus 3, right, plus x of minus 2 del of n plus 2 plus x of 1 del of n plus 1 plus x of 0 times del of n plus x of 1 del of delayed impulses plus x of 2 del of n plus 2, right, plus x of 3 del of n plus 3, and it goes, keep on goes up to infinity. For any value of n, this we already proved actually, for any value of n, only one of the terms on the right hand side is non-zero. Only one of the terms on the right hand side is 0. Rest all of the terms are zeros. By sample, you can substitute any one value. Let's say x of 0. So x of 0, then x of minus infinity times del of infinity. If the argument is not 0, then it is 0, plus dot dot dot, plus x of minus 3 times del of 3. Again, this goes to 0. Right, plus x of minus 2 del of 2 plus x of 1 del of 1 plus x of 0 del of 0 plus x of 1 del of 1 x of 2 del of 2 plus x of 3 del of 3 and so on. In this only one term is non-zero. Which term is that? This guy. This guy. This is non-zero because the argument is positive here. Sorry, the argument is 0. As per the definition, del of n is equal to 0. Sorry, del of n is equal to 1 only if n equals 0. It is 0 if n not equals to 0. That is the definition. That means argument should be 0. Now here argument is infinity. It leads to 0. And here the argument is 3. So it goes to 0. Here the argument is 2, 0. Argument is 1, 0. Then here also argument 1, 0. Sorry, here argument is minus 1. This is minus 1, right? Yeah. And here argument 2, 0. Here argument 3, 0. And so on. This all terms are 0 except only one term. Therefore, this also in more compact form you can write. Now the variable starts from minus infinity, not from 0. So in the previous case, when I wrote here, I put k equal to 0 to 3. Look at here. I put k equal to 0 to 3 here because my sequence is finite duration sequence. Now my sequence is infinite duration sequence. Therefore, my running variable is minus infinity to plus infinity. Okay, so x of k del of n minus k. So this is my x of n. So the moral of the story is this equation corresponds to the representation of an arbitrary sequence x of n as a linear combination of shifted unit impulses. Okay. Where when I say linear combination, then there are some weights like a times, when I say linear combination, a times x1 of t plus b times x2 of t plus c times x3 of t, like that we will write. So these are called weights. So what are the weights in this one? This x of k, the signal value itself. Okay, so the weights in this linear combination are x of k. So this is the weight. Weighted sum. For this weight, on the whole it is weighted sum, and this is the weight. To understand better, for in this semester you may have electronic devices, then mathematics, then signals and systems, maybe electromagnetics and waves. I don't know what are the other courses. Okay, so for this course the weight is 3. Suppose if you get A grade, then the credit hours is 3 times A. Mathematics in again 3 times. If you get A grade, you put A. In signals and system, 3 times. No, the weight is 4 here. 4 times, let's say A plus. Okay, EM waves, again the weightage is 4. So 4 times A, like this. So these are called weights. 4, 4, 3, 2. These are called weight. Weighted sum. As an example, this already covered in one of the previous lecture. Anyway, once again let me take it. Nothing wrong in that. Let's take x of n is equal to u of n. Okay, it's a unit step. It is the pulse with the unit magnitude and keep on goes up to infinity. 0, 1, 2, 3, 4. For negative values of n, this all are zeros. Okay, so in this case, u of n is equal to 0 when n is less than 0, and u of n equal to 0 when n is not greater than 0, greater than or equal to 0. So in this case, how do you use impulses to denote? This one is what? 1, because this all values are 1 only. So you times put del of 1, and this one is 1 times del of n. This is del of n minus 1, and this guy is 1 times del of n minus 2, and this one is 1 times del of n minus 3. So since the magnitude is 1, I put 1 here. Okay, so this is del of n plus del of n minus 1 plus del of n minus 2, del of n minus 3, and plus, and so on and so forth. So in more compact form, you can write this as, let me change the variable, k is equal to 0 to infinity del of n minus k. Here in the left hand side you have u of n. That's it. This is the more compact representation of your unit impulse. Okay, and take this equation k equal to minus infinity to plus infinity. Let me write down here one more time. X of n is equal to sigma k is equal to minus infinity to plus infinity u of k x of n minus k, not u of k, it is then some arbitrary signal, right? So why did I put u here? X of k times, again I did a mistake, some blend, stupid mistake I am doing, del of n minus k, x of k times del of n minus k. And this one is called a shifting property of the discrete time unit impulse. Because the sequence del of n minus k is non-zero only when k is equal to n, otherwise it is 0. Therefore the summation on this summation on the right hand side shifts through the sequence of values of x of k and preserves only the value corresponding to k is equal to n. For remaining all values it is 0. Okay, so this is the representation of a discrete time signal, that is arbitrary discrete time signal x of n in terms of shifted impulses del of n minus k with the suitable coefficients, and that coefficients are obtained from x of n, x of minus 1, x of 0, x of 2, like that. Okay, so therefore let me stop at this point. The next lecture we will talk about impulse response, then unit step response. If we give an impulse to a system, what is a response? And that response, that output is called impulse response. Impulse response, unit step response. It is fairly simple. You give del of n to a system, that system is LTI, and the output is called impulse response. That impulse response is denoted by a special symbol h of n. That h is always reserved for impulse response. Similarly, for unit step, if you give u of t to the same LTI system, then the output is called s of n. Okay, don't confuse. Okay, this s is already we used for complex frequency. If there is any ambiguity, then use a different notation. So it is not complex frequency here. don't confuse. Okay, when you give the input to an LTI system, the corresponding output is called an impulse response. When you give u of t, the corresponding output is called a step response or step output. Step response of an LTI system, and this one is impulse response of an LTI system. That's it. Anyway, we will study this in detail in the next lecture. Okay, so let me stop at this point. Thank you very much.